testing. Running.
Good afternoon. I would like to open this session on our senior design project presentations. Please take your seats. I would like to welcome here the members of our advisory board, of our undergraduate committee, and also the industry and laboratory mentors for our senior design project. Of course, I would like to welcome our students, faculty, and staff. This is very important session for us because we will show here the results of 1 year senior design projects. And I think we are very grateful to our laboratory and industry sponsors and mentors because this collaboration has been very beneficial for our students. So please enjoy the presentation and ask difficult questions to our students. With that, I am opening this session and passing to Dr. Mohamed Buram, who is the coordinator of Senior Design Project.
Thank you, Christian. Welcome to you all. And today we have 7 presentations, 7 projects, and each project has, on average, 5 students working together. They started in the fall on a 1 credit hour preparation, followed by the spring with full 3 credit hour preparations. This presentation will conclude all of their activities, so it is also their final presentation. There is no other presentation to follow, and they will come here in the corresponding sequence per section, section 1, 2, 3, 4, 5, and 7. We are giving each group around 20 minutes, 25 minutes, and maybe 5 minutes for questions. And if we consume the entire 30 minutes, then we will be, finishing in 2.5 hours. We may finish earlier. So I will call the first group to come forward and get ready to do the presentations. Thank you so much.
All right. Good afternoon, everybody. My name is John, and I'm here with Tyler, Nathaniel, Kinley, and Kai. And this year, our group studied, and our project was the simulation-driven autonomous control for a small modular reactor. So the small modular reactor that we did our project on was EBR2. EBR2 is an experimental breeder reactor. It is no longer active. It's a liquid metal fast reactor that uses sodium as its coolant. It is 62.5 megawatts thermal, and the minimum thermal limit for our project was 700 degrees Celsius for the clad temperature. This is because at 700 degrees Celsius, the cladding will start to melt, and the reactor contains 3 loops. Our project will focus on the primary sodium loop. And there are 2 pumps on this loop, and the 2 pumps are rated at 5,500 gallons per minute. So the project purpose is to develop a conceptual design of a nearly autonomous controlled reactor. We are doing this because it saves cost, it maximizes safety, and Tyler will get to that more in a later slide. And why NAMAC? So NAMAC stands for Nearly Autonomous Management and Control. And the reason we're doing nearly autonomous rather than full autonomous is because if the AI was trained for certain situations and none of those problems seem to have occurred and a different problem occurred, the AI might not be able to diagnose and prognose correctly. So we'd still like to have some sort of human interaction there to make sure that the correct problem is diagnosed and prognosed.
Okay, so as John touched on, The reason why we are interested in implementing autonomous control is to maximize the safety of reactors and also reduce the operational costs. So in terms of safety, if you implement an autonomous design, machine error is much less than human error. This is just inherent. It's seen today when you use self-driving cars, like Google's self-driving car, which has driven over something around 10 million miles without being in an accident that was deemed its own fault. So machine error is much less than human error. In addition, one of our advisors that we work with pointed out that if you use autonomous control, you can keep your reactors in more isolated areas, such as deep underground, as well as actually even underwater. If you do this, you can reduce your security costs because you have more natural security. It's harder to penetrate a nuclear reactor if it's underwater or underground. On the other hand, in terms of reducing the operational cost, you can, sorry, what? Oh, okay. So if you reduce the operational costs with an autonomous reactor, it's because an operator is not necessarily needed. We're using NAMAC, so we will use an operator, but instead of one operator controlling one reactor, you can have one operator control multiple SMRs if you have an autonomous system, and that'll reduce your operational costs. So we could have showcased our autonomous design with a number of different accidents. The accident we chose to do was a partial loss of flow, or a LOFA. This is because our reactor is a pool-type reactor, so a loss of flow is a much more common accident, rather than a loss of coolant, which would actually require a hole in your containment or something like that. So more specifically, our accident scenario was due to a partial loss of one of the primary sodium coolant pumps in speed. So if you have an autonomous system, the most general and complicated algorithm that you have to work with is seen by this flow diagram. So you take output from your reactor system and its digital twin, which is a thermal hydraulic code, which we'll talk about later. We use that output in a sorting algorithm to determine whether or not your reactor is operating in nominal or not. If it's not, then it's then passed to a diagnosis phase. In this phase, we test fault trees, and this is a complicated algorithm that we didn't primarily focus on. So we test a bunch of different faults, and after the diagnosis phase, when it has determined the accident, it updates a fault tree, which is it's a tree of all the probabilities of every accident that could possibly occur, and it updates the accident it determined happened to 1. This initiates the prognosis phase, so then your reactor uses its digital twin, the thermal hydraulic code that it's coupled with, to test different control options. And then it will test things like the damage to your reactor, the margin to safety, your economic loss, and it will determine what is the best control option based on utility functions that that company will use. So these things are very complicated. It will choose that control option and then implement it. Okay? So basically that was just too much work for 2 semesters, so we decided to make some simplifications. We simplified it by pretty much eliminating the diagnosis phase. So we assumed that the error signal from the loss of the reactor coolant pump was perfect. It didn't ever fail, and it never outputted a wrong signal. So we made that assumption. We also assumed that there was only one accident, just a loss of flow. So we really didn't have to deal with the complicated diagnosis algorithm. We focused primarily on prognosis. In addition, we also assumed that there was only one control option. We assumed that the way to deal with this partial loss of flow was to increase the pump speed of the non-effective pump. So that eliminated the need for the complicated utility functions in the prognosis phase. So after that, this is actually a more simple, although it looks more complicated, it is a simpler because this is just a more in-depth version of the prognosis phase, which talks about taking output, training your data, and then using it to machine learn and predict what control option is the best, and I will let Daniel and others talk about that.
Okay, so as we mentioned, we used all these different software packages and frameworks to complete our design objectives. This program or software package framework known as Raven, it pretty much was our basis to create a knowledge base or database so that we could even train our machine learning code later on. Now Raven does have quite a high learning curve to it for anybody who's interested in knowing, but it can plot, predict future states of plants. It can limit surface, different distributions, Monte Carlo, grid, you name it, it can probably do it. It's developed by Idaho National Lab, but I'll just reiterate, the reason we were using Raven was to perturb specific variables in our GOTHIC model for different outputs is what we were looking for, more or less, and you'll see that later on. So I mentioned this code known as GOTHIC. It's the general purpose thermohydraulic software package developed by Zachary Nuclear Engineering. And it's primarily used for containment modeling, but we decided, well, EBR2 doesn't really exist anymore, or doesn't run, so you can't really test what we were looking for, so we have to model it. Now, the model was provided by Zachary Nuclear Engineering, and all it really does is we have an initial state, steady state, we run our steady state, then we perturb some values, and it continues to run for, I think we ran 780 cases, I think were the different variables. But the primary takeaway you should know about GOTHIC was it's solvable for mass, energy, momentum equations, and it was the primary basis program for our model to ensure that it works correctly. So you're probably wondering what the GOTHIC model looked like. Now earlier you saw a picture of EBR2 and how kind of like the sodium flows through it. So this is just the primary loop. You'll see, well, it's kind of hard to see, but way up near the top you'll have the intermediate heat exchanger. These funny looking whistles here are your primary sodium pump 1 and primary sodium pump 2. And then the big box here is the primary tank. And like I said, we're pretty much focused on what happens when primary sodium pump 1 loses a percentage of speed and how we mitigate it with primary sodium pump 2. And so here's just some of the data that we were able to collect and the results we were able to bring out of the model. So you'll see that you have two different cases here. When pump speed fails to 25% and to 50%, you actually see pretty much the same trend, but the amount of temperature that you're getting that is lower is actually different. Excuse me. So you have a legend. Legend is relative to pump 2 speed. So here you have 1.47 is you've ramped pump 2 speed up by 47% of what it originally is operating at. And you'll see as you get more and more higher values, your temperatures are actually decreasing, which we should expect because we have more of the, we're able to continuously keep the sodium flowing through the fuel, over the fuel. Again, you pretty much are going to see the same trend. This is just the upper plenum temperature near the top of our active core. And once again, lower plenum temperature, I find it quite interesting that, as you saw in the upper plenum, you have the blue lines were actually your lower relative pump 2 speeds were actually near the top, so they were actually lower, but here we have them reversed, which is expected. And then more results for relative pump 1 flow rate over time. And actually, as you can see, we actually do have backflow through the first pump.
Okay, so we have this thermal limit of 700 degrees Celsius was what we put on here. So here we have a flow diagram as to how we would look for a solution where we can find whether or not the pump 1 speed decreasing is going to affect the system the system pump speed such that can pump 2 speed compensate and prevent the clad temperature from reaching that 700 degrees Celsius. So what we have is we have the readings from the upper and lower plenum temperatures, and then we also have the mass flow rate readings from pump 1, pump 2, and the Z pipe. And then we use a feed-forward neural network to predict the fuel temperature. And we could also predict the pump 1 speed using the regression. We can use a regression analysis neural network
and we can actually have predictions for very short time spans of like 2 seconds. So MATLAB is actually really convenient to use machine learning, where it has different modules for multivariate regression analysis and classifier modules. Here, for example, is how MATLAB would take 4 inputs and then through a black box would produce an output that would predict an outcome based off of the training data that is provided into it. So to predict pump speed 1, we had 23 variable inputs, and these variable inputs vary from the actual readings from the temperatures of the coolant to the differences over time and the gradients from the inlet and the core outlet. And we have this anticipated interval of prediction for 2 seconds because we want to have a very short time span where if a transient scenario were to occur, then we are looking for the smallest amount of time possible to actually act upon the transient and prevent it from evolving and getting worse. So here are some of the parameters explicitly listed. For example, you have the upper plenum temperature and the high pressure and lower pressure, lower plenum temperatures and the mass flow rates. Here we have the absolute differences between the lower and upper plenum temperatures, and that is to reflect the axial temperature gradient along the core. And you want to have a very specific nominal temperature difference from the bottom, from the inlet to the outlet. And you can actually design control based on this. So using the regression analysis network, we found that in 65 iterations of using the training data versus the targeted input, it found that it would converge pretty quickly, and it shows that the errors were actually pretty small, such that it was capable of predicting, even in 2 seconds, what the expected pump 1 speed would be.
So following finding what the pump 1 velocity is, we use that as an input along with a few temperatures listed on the screen behind me to calculate what the centerline temperature would be, since a lot of thermal limits are based on centerline temperatures and, or in our case, also clad temperatures. So this one was also done with a Bayesian regulation such as the last one was, and so this one was, the goal was to find the centerline temperature. Why you not move? Right. So this one, you can see the training. It was very good training. It ran quite a bit longer, so it didn't reach such a small gradient as the last one ran. But after 1,000 iterations, we have a mean square error of 1.13 to the -5th. And the plot on your guys' right, so right behind me, shows the bin that the error falls into. So and the yellow line that hopefully you guys can actually see, it shows where the 0 marker is. So all the bins are more or less directly on top of 0. And so what we use the centerline temperature. So what we use the centerline temperature for is in tandem with the pump 1 velocity and what we need to find pump velocity 2. So this network is a bit larger, and it's actually, we use a different type. So as you mentioned before, there's classifier or pattern recognition and the fit networks. So this one uses the pattern recognition, so the error function and the training method and activation functions was slightly different for the purpose of this network. And in this network, what we would do is we would feed 3 inputs. So you'd have the centerline temperature, pump 2, you'd make an array of pump 2s for the outputs, and pump 1 to figure out what cases of pump 2 actually succeed. So the results from the training behind me are, you can see that the neural network could use a bit more fine-tuning, but it works, and it actually reaches a low gradient, again, just the other one. So it ended at 93 iterations, and all the errors fall more or less directly around 0. So what are the inputs and the outputs? Visually can be seen behind me. So on the left are the inputs where you have centerline temperature and you have pump 1, and then all the blue dots are success cases, and all the red dots are failure cases. And this is for 50% pump speed. So this would be one of the sets of data you use for training. There was actually 3 of these to get the 768 data points that Nathaniel was talking about for the training. So the right side is what would actually be going on during operations. So once we know what pump 1 failed to, in this case it's 50%, and we can just calculate the centerline temperature. In this case it was 150. We can now find with 32 allocations of what pumps velocity 2 should be. And then we have a script that runs through it and finds the first success case, which for sigmoid is anything above 0.5. And in this case it was 1.2258. So we had quite a few technical challenges with this project. One of the biggest ones was time, as mentioned by Tyler. So a lot of simplifications came from that. A few other ones we ran into was actually just manipulating large data. We realized you'd be very specific with formats, or you spend training the exact same numbers because it doesn't save all the decimals. And also another large issue we found into how to work on is all these parameters even related whatsoever. And it seems to be from the training of the neural networks that they all correlated and that they did show what we wanted them to show. So some of the future work and conclusions that we have is that we were able to find what the pump 2 velocity should be to succeed the case. So what we would like to, or what future work could be done on this project would be, instead of having 3 bins for pump 1 failure, make it a continuous function. And then beyond that, even having other accident cases. As the simplifications mentioned, we don't take into account anything but pump 1 failing with 100% accuracy that we know that pump 1 failed. So just future work just to make it more generic to take into other kind of accidents that also fall into the loss of flow and even other accident cases. We would like to acknowledge Dr. Din and a few of the postdocs that helped us with this project, and our industry advisors from Zachary Nuke Engineering and from Idaho National Labs. Any questions?
Questions for this group?
Yes, so
Susan.
I'm Susan Hines, I'm from Southern Nuclear, so you know who I am. So I have 2 questions. First, what kind of margin to your thermal limit did you allow yourself, to your centerline temperature? And also, I noticed you calculated quite a number of significant digits on your increase in pump speed. Is your pump, are you actually capable of controlling to that?
So for your first question, what was the first question again?
The first question was, how much margin, if any, did you allow to your centerline melt?
All right, so
Acceptance criteria.
for the limits, for this we just show that it can, if you set a limit, it can calculate to that limit. What you choose, so that limit can arbitrarily be set to whatever margin you require. So that could be a train. So for this one, it was set for 690. So that was actually even below the CLAT's temperature limit. So you can change it to various. Since this reactor, you don't have to adjust it. We had to set the limit so low because one of the effects of the EBR2 is doing nothing is safe. So because of that, we had to make sure, actually show that otherwise all the dots would be blue and we couldn't train anything. So we set the limit fairly low. So it actually has quite a large margin on that.
And
Second question.
can you repeat the second question?
The
one more time?
second question had to be with the value you
Oh, the second
calculated
thing.
for the increase in speed. You calculated, I forget, 5 or so digits after the decimal place. Can you really control the pump to that level of precision?
So that one actually came down to just, when we ran the code, there was 32 nodes, and that was just linear spacing between what the pump was trained to from 0.05 to 0.5. So that just happened to be how the linear spacing worked out. So I do not believe the pump can be controlled that detailed.
Other questions, please? Yes.
Alan Eisenhower, Oak Ridge National Lab. This is not a real technical question. It's more kind of a philosophy implementation because I was reflecting on one of your comments that you made. And I'll also say I'm all for autonomy. But you made the statement that one of the reasons to strive towards autonomy is the machine error is less than human error. And in some cases, that might not be a good thing. For example, the 737 MAX, right? And so the question, and I don't, it's kind of open-ended, but I wonder if you thought about it, but how do you actually implement this? How do you train the operators in an environment where there's so much more dependence on the machine to drive the reactor? And how do you overcome that when you have bad sensors and things like that?
So that's the one thing you have to take into consideration. So the code outputs a suggestion. This is an option. It's not something you have to do. So the idea is, if you have one operator, most reactors you wouldn't be, potentially more than one could have an issue at the same time, but hopefully no reactor would have two if you have multiple reactors having an issue at the same time. So you only have one reactor having an issue, so they can focus on that one reactor. But it spits out a suggestion that you have to do. So it's not a, hey, this code found this, do this right now. It's a suggestion. Would you like to expand, Tyler?
I was just gonna add to that. Yeah, that's a big ethical question as well with autonomy. You see that in discussions about self-driving cars is whether your reactor saves the pedestrian or it saves the driver. And so things like that haven't really been addressed as so far, but probably would come down to actual like legislation and law, like how your autonomy would have to occur.
Yes.
So I'm John Strumpel, I'm with Plenum, and my question is similar to Alan's, but trying to get, I think what he's trying to get at too was, so it's going to give you some information, the operator, and the operator's got to make a decision whether he's going to use this information or not. So did you think much about, can it give any information on the basis or why it's pointing in this direction so that they can make an informed decision, help get some sense of whether or not it's trying to, you know, as he said, pull up or push down or
Well,
whatever.
what we could do is we didn't actually consider that, but so since we didn't really do too much with diagnosis, the main thing our diagnosis did is just which one of the 3 bins it fell into for the pump 1. But it could give the operator more than just, hey, change this. It could be, this is what we think the error is. Because of this, you should do this. You have a list of options. So you can output, theoretically you could output, this is what we think is wrong, and this is why this should be the opposite. So why that's the option it picks. You could, based on the training you gave it, so you could output more than just the suggestion.
I'll add something as well. So, one thing I talked about was the utility functions, and that so basically in a more complicated system, you'll have several control options, and those will be based on, and those will maximize your utility. So, like your utility will just be some net positive that your company chooses, whether you want to weigh safety more, or you want to weigh economic loss more, something like that. So, you will basically choose your utility function, and based on what you choose is more important to you as the controller of the plant, it will tell you what is the best decision. So that has to do with the utility function that we didn't address because of time constraints.
There was another question here. I think there was another question. No? No more? Well, let's thank the group again. So, let us get section 2 to come forward, please.
Right, Jacob, do you know, where do we upload it? Where was it saved at?
When you get out of this, because we are.
Yeah, let me help you out here. Yeah, okay, thank you. Group 2, right?
Yeah,
Yeah.
group 2. Okay, you are ready. All right.
Okay, have fun. Watch the keel.
All right. Good afternoon, everyone. My name is Dami. This is Jacob.
Closer, so
Oh, sorry.
loud voice.
My name is Dami. This is Jacob. This is Devante, Kiara, and Trevor. We're presenting on the optimization of a small modular reactor equilibrium cycle. So a little bit about our reactor. Here's a diagram. It's 160 megawatt thermal, 60 megawatt electric, 37 assemblies, 17 by 7 array, which you typically see in traditional pressurized water reactors. So a little bit about SMRs versus PWRs. PWRs are typically economically better because of the large economies of scale, whereas SMRs, like you have to, like if you, right now, it's like you produce it and then it's not like assembly line, so they're trying to make it more assembly line so that it's more economically feasible. And so in addition to that, a big part of our project was optimizing the neutronics of it, so fuel enrichment, loading pattern, yeah. So more about the current state of SMRs. The Department of Energy has expanded plans to build 12 60 megawatt modules by 2026. So one of the SMRs that are going to be built we want to have it designed so that its low following capabilities can be used for auxiliary things such as thermal energy, desalination, and hydrogen production. So basically, I know most of you are familiar with load following, but if you increase like your turbine demand, let's say for example 60 megawatt, and your reactor power goes up to like 80 megawatt, you want to take that extra 20 megawatt and use it for some of these things. So only one of those is going to be used for that. So a little bit more about NuScale. So it has an integrated design, which in technical terms, that means that everything's contained within the reactor pressure vessel. So something like LOCA, it would be contained within the reactor pressure vessel, and also natural circulation where you have your heat sink very low. It'd be designed so that your heat sink is low enough to accommodate for this accident. So a little bit more about the project. We're going to be designing a 3-batch equilibrium cycle, which means you have once burned, twice burned fuel, and your fresh burn fuel, and we're going to be arranging those to optimize the loading patterns. Some of our degrees of freedom are we took, like you'll see later in the presentation, that we took NuScale's reactor, and so we got their loading pattern, but we did things mainly with like the enrichments, loading pattern, and burnable poisons to optimize the neutron economy. And yeah, the big part about optimizing that neutron economy is we want to compete with like average cost in the US. So it's again about balancing that trade-off with building like a big pressurized water reactor, and we have this smaller modular reactor that we want to like I guess optimize more by using neutron economy. So.
As you can see, we used the safety limits provided by the NRC. Our reactor was a 3-batch equilibrium cycled reactor, meaning that it used a fresh, once burnt and twice burnt fuels. The first and second being switched out in the assemblies, and the third being the spent fuel. Our goal was to have a depletion cycle of 2 years, 730 effective full power days, and to have it be the cheapest as we could possibly be, meaning that we try to lower the amount of enrichments and increase the amount of effective full power days if we possibly could. We used the Vera coding system. Vera was better to use than Castle for the simple fact that it's more efficient to use for the smaller variants of nuclear reactors. It's also it uses integrated sources such as Impact, Bison, and and Mamba to be able to provide solutions for advanced problems in the industry. The trade-off with using it opposed to other coding systems is that it has a higher computational demand. So, for instance, we were allowed to have 111 computer cores to be able to run our code. If we tried to gain any more, we would have been held in a queue where we would not, where it would sit in, but it wouldn't actually get run. It would just stay in that queue for as much time as possible. The downside with these also is that the amount of time that it took to actually run a cycle was around 20 hours, which is way longer than we actually wanted and could possibly want for it. Here's some of our input parameters. As you can see, it's around 500 degrees Fahrenheit for the temperature and a pressure of 1850 psia. Our fuel pins, these are in centimeters for our fuel GAT and zirconium alloy 4. As you can see, for our depletion steps, we go 0, 1, 3, 5, 10, 15. That is because we wanted to have a more refined production from the initial effective full power days. As you can see on the right, there is our radio map. For each one of those numbers that you see was one of the computer cores. So that's where that computer core, that's the region that it actually computed. If you see the 0, however, that is the blank space from the outside. And there's also there's 3 radio regions and 37 actual regions, which produce our 111 cores. As I said before, one of the downsides was the significant run times, which is around 20 hours. Because of this, it didn't really allow us to use the optimization algorithms, because the algorithms would have went through thousands of iterations, and at 20 hours each, it would have made it an incredibly long process. So the only option we had was to do it manually. The 2D versions that we did ran at a faster rate. However, they didn't produce very accurate results compared to our 3D models, which ran, of course, longer. Additionally, we could have split the core in half and set the core as a boundary and assume that it'd be perfectly reflected.
So as Devontae said, we looked into 2D and core splitting techniques, but we quickly realized that core splitting wasn't very viable due to the fact that we have core thermal hydraulic asymmetry in the axial region, and additionally just splitting it in half would theoretically only cut the number of computer cores needed in half, and that means the run times wouldn't be that much better. So the cost benefit wasn't that great for core splitting to begin with, so we axed that pretty quick. But we decided to look more into the 2D case. So as you can see here on the top right, we have a GIF of the 2D versus 3D power distribution over depletion. So if you look, when it's initially red, that's at the hottest regions, and as it depletes, you can see that the core evens out over time. And you can see in the power distribution, at the initial state, it's not very representative. The 2D model is not very representative of the 3D, but at the end state, it actually becomes quite good. And as you can see over here on the Boron Letdown curve, it actually converges to a similar value. And this core loading pattern was just kind of an example that we did to see if the 2D was representative of the 3D model. So we could take this 2D model and we could essentially work backwards. We could pick a loading pattern enrichments, do a full depletion, see what it came out to at the end of cycle, and then work back and figure out what enrichments we would need to move on to a 3D more refined model. So using this, some of our initial core designs are given here. In the top left, the initial idea was to create what's known as a sort of ring of fire to reduce peaking. So we had an extremely low enriched assembly in the middle, and then we had sort of 2 rings around the outside. But the peaking was very hot near the center assembly. As you can see, our total peaking factor is 2.41, and our hot rod peaking factor is around 1.56, which are both above our limits. And to lower the peaking, we went on to several other iterations and moved on to this other core design at the bottom, which did lower the total peaking to 2.18 and the hot rod to 1.46. But again, our total peaking was still significantly above our limit. So this took a couple months to develop, just guessing, basically moving enrichments around. So we realized with the end of semester deadline that we weren't going to be able to create a 3-batch equilibrium cycle in time due to the significant run times. So we began looking at more published data to see if we could find an SMR loading pattern to kind of begin with. So this is when we found NuScale's SMR's loading pattern. And as you can see, the blue squares are the fresh assemblies, the red are the once burn, and the yellow are the twice burn. And here are their safety parameters. So they do meet our design constraints. Their total peaking factor was 1.86, hot rod peaking factor 1.4 about, and their average linear heat rate was about 2.5. So now we had something to go from and to see if we could actually better this design and improve upon it. So using this, we come up with this design here. But again, our total peaking factor was about 2.23, but we realized it's really hard to tell on this, but there's a pin right here in the very top left corner, which is the only pin that's actually above our limit. So if we could put GAD, or probably place GAD in the K6 assembly, then we could hopefully reduce this peaking and then move forward with an actual usable core. So we found out that iterating through the GAD placements in the K6 assembly was the best method for developing this core further.
Okay, so here is our final fuel loading pattern that we achieved based off of what we can tell from NuScale Power's design. We have fuel assemblies with 3 different enrichments, the highest being 4.5%, and enrichment is constant axially. So only the C2 assemblies have gadolinium in them. We tried to minimize the amount of GAD that we used in order to maximize our fuel efficiency, and we found that the GAD was really only necessary in that C2 assembly to mitigate the peaking. This appears to be an improvement from what we can tell over NuScale Power's design, where the only thing that we know is that their maximum fuel enrichment was 4.95% and the max GAD weight percentage they used was 8%. Here's a model of how core power behaves through the first cycle. The distribution is relatively uniform, although you can see that as the fuel begins to approach the end of cycle, there is that peaking in that middle right assembly, the C2 assembly, which is what we added GAD to. The addition of gadolinium rods to this assembly keeps the peaking well below our safety limits. And if you look at the axial power distribution, you can see that there's really not much to note except for the fact that you can tell towards the edges that the fuel is just not being burned quite as efficiently as it is in the center. The bulk of our design iterations were actually not focused around keeping our safety parameters from the band so much as it was to try and minimize our boron concentration, which is surprising because this is an SMR, so we were really anticipating that peaking factors were going to be our limiting parameter in this design. So boron concentration is limited in its initial state based on the requirement for a negative moderator temperature coefficient, but actually what ended up being our primary focus was trying to minimize our end-of-cycle boron concentration. So for our final design, our end-of-cycle boron concentration was about 24 parts per million, which is as close to our target of 0 as we could get it. The most limiting safety parameter in our design was the hot rod peaking factor, which had a maximum value of 1.35 when its limit was 1.5, and the max power peaking factor was 1.6 or 1.96 with a max value of 2. So on the right is a plot showing how these peaking factors behave through the fuel cycle. They are most limiting in their initial case, although you can see about halfway through the cycle there is a second peak, and that's due to the burnup of GAD in that C2 assembly. So for our safety analysis, VeraCS is a core simulator, not a full plant simulator, so we couldn't run many of the traditional accident cases like LOCA or LOFA. So instead what we did was we calculated reactivity coefficients and the reactor shutdown margin. The isothermal coefficient was the first reactivity coefficient that we calculated, and the safety limit associated with that was just that its value had to be sufficiently negative. The isothermal coefficient was selected at the recommendation of Dr. Palmtag as a substitute for calculating moderator temperature coefficient, just because the moderator temperature feedback can be difficult to distinguish at high powers from the Doppler feedback. We found the isothermal temperature coefficient to be minus 1.6 ppm per degree Fahrenheit in its initial state, and as we saw before on the previous slide, the boron concentration really peaks in the beginning of the cycle and then decreases from there. So we know that isothermal coefficient is going to be most limiting in that initial state. So we know that by looking at this value that we have satisfied this safety requirement.
The other safety parameter we checked for was the power defect. That is the combination of the moderator temperature coefficient and the Doppler coefficient, along with a couple other minor things. We ran it on a scale of percent power, and we actually had a anomaly here and some at the end at the full power ranges, and this was due to convergence issues inside of Vera's software. We ran a updated case, Dr. Palmtag ran an updated case and had it run. But when we submitted it to the Henry 2 cluster we used, it sat on the queue for over 48 hours and never submitted. So what we did was we used a polynomial line fit to approximate the lines, because you only have 1 or 2 anomalies inside of it, so the line will fit very appropriately on there. And from there we could get our power defects, total power defects, by integrating the lines over the whole power range. From there, we could do our shutdown margins for BOC and EOC using the total worth of all the rods, the highest and then neglecting the highest worth rod and removing the insertion limit and accounting for our certainty, we could find our total control margin. And then from there, we added the power defect and could find our shutdown margins. And EOC was the most limiting, but even still, it was well above our minimum shutdown margin we needed, and as well as our other parameters, including exposure and peak linear heat rate. The economics of the SMR, which in essence was the most important goal of this project, showed with our lower enrichments that we could get a break-even cost of 12 cents per kilowatt hour, which is the U.S. national average. But there are other states that pay over 20 cents per kilowatt hour that have more remote locations like Wyoming, Montana, those areas. They have higher fuel costs because you can't put a 1,000 megawatt electric plant out there because there's not enough people on a single grid to reach it. But with SMRs, you could put it in smaller areas where they could have a break-even cost that even after adding for profits, it would still be lower than the fuel costs they are paying there currently. The big cost for us was the operations and the reloading costs, because the fuel costs were very small because we had that center assembly that was only 2% enriched. We only put in 9 assemblies every cycle instead of the whole core. In all, the Vera software was very user-friendly, helped us find full resolutions, and helped us find all the numbers we needed to, but is not ideal for the iterative design that we were originally going for to optimize. It modeled NuScale's current SMR very well because it has a pin-by-pin resolution instead of assembly resolution, but it helped with the economic cost and safety parameters too. We were able to achieve the lower enrichment than at NuScale's designs and lower safety parameters than NuScale's design, and we were still able to reach the 2-year depletion and having a lower peaking factor as well. Our future goal that we did not have the time to get to was changing the axial assemblies or axial enrichments inside the assemblies. We were going to add natural uranium blankets for the top few and bottom few pellets in there because they were not being, the high enriched fuel was not being utilized, and that's just wasted cost. So we were going to add the natural uranium, but we ran out of time. We know that this would increase the peaking factor, but where our peaking factor is so low, we have sufficient margin to play with the peaking factors. We'd like to acknowledge Dr. Anastratov as our project advisor, Dr. Palmtag as our Castle advisor, and Oak Ridge for allowing us to use their supercomputer cluster for our early designs. Any questions?
Sure, there will be questions. Yes. Questions? Yes.
Mike Sabella, Framatome. I noticed all of your core designs put the fresh fuel around the core periphery. You tend to lose a lot of neutrons from leakage at that point. Did you look at any designs where the fresh fuel was interior and see if you could optimize the economics on that?
Peaking was very, very hot to do that. The only way that we managed to keep peaking low was to put it around the periphery, which again does hurt neutron leakage, and it would hurt from embrittlement of the vessel and stuff. But this was essentially the only loading pattern that really worked. They have the fresh really around the outside.
Susan.
So Susan Hoxie, Southern Nuclear. So at a utility, you would be looking at number of assemblies, enrichment cost, and uranium cost. So you might make a decision to actually have higher enrichment or have more assemblies and lower enrichment. Did y'all vary the number of assemblies that you looked at? I know you ended up saying you had 9 fresh. Did you look at any variation in number of fresh assemblies, and also what was your source for your fuel costs in terms of uranium conversion enrichment costs?
The initial cores we did test because we had no prior equilibrium design, we did test different numbers of fresh cores, and some of them that were higher, the peaking was too high, and then some of them that when we used lower than 9, it didn't reach the 2-year cycle because of the neutron leakage. If you have all of it on the inside, the peaking's too high. If you put too little on the outside, all the neutrons aren't used effectively for fuel, and it burns out before the 2 years. And for the economics, where was the source? We used a paper mainly from Castle that was a conversion that compared full-sized reactors to SMRs. And those because fuel cost is by kilogram uranium, it doesn't matter the amount of it. The fuel costs were the same. We used their numbers, but we also, for the other operational cost, reloading, all those things, we used it because we use that source because they did it by a % of total operations of the plant based off the fuel cost. And since we use the fuel cost as those percentage basis, so our operations, maintenance, capital, and all those other things, because it was a smaller plant, we still use the same percentages relative to the fuel cost to get those numbers we had.
Questions? Any other questions? Any other question? Yes.
I think the purpose of using 2D calculations versus 3D was we weren't actually looking at boron concentration where we were testing the 2D parameters. So we did recognize that 2D boron was way higher, but we weren't looking at those parameters when we were testing it. So I think when we tested it for what we were looking for, the fuel enrichments, we tested to see if it modeled the 3D accurately, and then we actually run a 3D.
And I'm going to add as well that the 2D model was a slab that we were using, and it was modeling that as a critical core. It wasn't doing an approximation with the 2D, it was modeling that slab as a full core. Yeah, that was the full size of the core was the 2D model. So it uses boron, it searches for the boron concentration to make it critical. So that's why it was lower.
Any other question to this group? No more? No more? Okay, thank you. Section 3, please come forward. Come on. How are you?
Give me 1 second.
Yeah.
What?
Lars is not the iPad used for class.
No, my iPad's a curse, man. I'm telling you, it's terrible. Never again. But you are using my Mac, so say nice things. I'm sure they're listening. I'm sure someone in Cupertino is listening in.
Daniel got through it. I think I can get through it.
You good to go? Let me load up your new talk here.
Number 3,
Yep.
section.
Group 3 presentation.
Group 3.
Yeah, so.
This is it.
Oh, it's already up in
Yeah.
presentation mode. All right.
Okay. You are ready? Yes, please.
So hello, we are Group 3. My name is Matthew, this is Carthiga, Jesse, Scott, and Graham. And our project is making molybdenum-99 production in the NCSU Pulsar reactor.
So in this presentation, we will talk and discuss our design objectives, our motivations, our target designs, our core design, our assembly design, our accidental analysis, and our economic feasibility study. The sole purpose of this project is to try and produce molybdenum moly-99 in the pulsar reactor. In order to do this, we have to replace a normal assembly with a uranium target. Once the target is irradiated in the reactor, it will cause the uranium to fission, and then we have moly-99. Within doing this project, we have to maintain and verify that we are in compliance with the NRC safety standards. So moly-99, it decays into technetium 99 metastable, and that's used in about 2/3 of the medical procedures here in the United States. Moly-99 is sold in 6-day curies, which are activity of 6 days after it's removed from the production reactor. Currently, there are only 7 reactors in the world that produce moly-99, and one is not in the United States. The world's approximate use is about 12,000 6-day curies a week, and the United States uses approximately half of that.
So the first thing I had to do was determine how are we going to have a target, how are we going to make it and get it. And in doing that, the two methods we were able to find are using uranium-235 fission or MO98 neutron capture. So we have both of those reactions listed here, where the uranium will take the neutron, it'll fission, making MO99 with approximately 6.1% of the yield, and then other fission products. And then with that, since we're only worried about the 235 there, it can be high enriched uranium or low enriched uranium. The other option is our MO98 capture, where we'll have our MO98 target, and we'll capture the neutron, making MO99. First thing we want to do to look at it was say which of these two methods would be the best to use. And so we looked at the cross sections of that. The neutron capture cross section for MO98 is around 180 millibarns, versus the U235 fission cross section of 585.1 barns, which is about 3,000 times as large as the MO98 capture, which means you would need about 3,000 times more mass of MO98 to make the same amount of MO99 as if you had fissioned uranium. So once we knew that we were going to use uranium, we were able to say how will the uranium become the MO99. And in doing that, we'll have our mass of uranium in the target, and then we'll be fissioning it in our reactor. And then our MO99 will be created from the fission, and its half-life is about 66 hours. So while it's in the reactor being created, it will also be decaying away. Once we have that, we can figure out how much mass of 99 can be created over time as a function of how much 235 is initially in there, how much flux we have, etc. And then we had to figure out, based off the amount of MO99 we have after those 7-day irradiation period, what's our activity going to be after 6 days for the 6-day curie. So then we have a graph here showing that how MO99 is going to build up while it's being irradiated. It's being created faster than it's decaying away. And then once we move it from the target, it'll be decaying away for our 6-day curies. We had determined that we were going to use U235 fission, and in doing that, we either want to use LEU or HEU. In the world right now, they're using HEU targets, which means they need a smaller mass of total uranium. So here we have a graph showing the mass difference between HEU target and LEU target. They'll both use the same amount of U235, it's just the total mass. So assuming a flux of 10 to the 13th neutrons per centimeter squared second, we would need approximately 500 grams of uranium, or 2,300 grams of uranium if we're using LEU if we want to produce 2,000 6-day curies a week, which is 1/3 of the U.S.'s demand. And in doing that, our main consideration for doing this is proliferation reasons, we want to use LEU. We don't want to be using HCU if we don't have to be. But also, it's a lot cheaper to have LEU enrichment than HCU enrichment. Then once we decided we wanted to use LEU target, we had to figure out what's the target going to look like. Through our research, we found that in use, or being researched to be in use, they have plate type targets, uranium aluminum dispersion targets, or metallic uranium targets. Our main variables here for our consideration were, we've got a small reactor for the Polestar. We want as much U-235 as possible and as small in total volume as possible. So we wanted to maximize our density. And in doing that, we decided that a metallic uranium foil target will give us the best chance of doing that. So then this is where we got the metallic uranium properties from. This is for a Pakistani research reactor that they're looking at the target, where you'll have a outer metal sleeve with plates both at the top and the bottom of it that will allow it to fit in the reactor. Along the bottom of the sleeve, you'll have crossbars in which the inner cylinder will sit. The inner cylinder is what's actually going to have the uranium and the other components of the target itself. So you have channels around that allow water to flow up, which will help us with our heat transfer and prevent our target from overheating and melting.
Okay, so as we mentioned, we are going to be using the metal foil for our uranium target. Currently, different types of metal foil uranium targets that are being used or researched are cylindrical in design, and specifically the one that we were modeling for our project was going to be from a Pakistani research reactor. We also saw that this type of target was being used at the Missouri research reactor. They're doing some tests with it. So some key dimensions that we have from our target. First of all, for the materials, it is an aluminum cylinder target with a nickel foil in between the uranium foil. And the nickel foil is there just as a fission recoil barrier to make processing the target after irradiation easier. And as we mentioned, the Polestar reactor is very small in total volume, so we needed a relatively small target. And as you can see here, this target is only 2 millimeters thick and 14 centimeters tall. So if needed and we were not be able to produce as much moly as we wanted to, we could add more targets depending on safety analysis. And as we said, we are going to be using an LEU target. So for this design, with a 19.75% enrichment, we can get approximately 8 grams of uranium within the target. So to actually model this project, we had to figure out that we're going to have to computationally do this because we're not actually going to be able to put something into the Polestar, remove assemblies, and do that within the span of 1 year as a senior design project. So we are going to be using Scale, and specifically within Scale, we're going to be using Kino 5. And Kino 5 was just going to be our geometry package along with Monte Carlo simulation, so we could do our criticality analysis and also be able to calculate reaction rates and flux within the core and in the target. In addition, we had to develop the whole model for the Polestar and also our changes to the Polestar core because the current configuration would not be optimized for production. Once we had our core designed, what we had to do is also model specific elements such as absorber rods, which we'll talk about more later just in terms of our safety analysis. And finally, after we had all this completed, we could calculate reactivity of our target and do our safety analysis on it and also see what kind of production capability we could actually have. So for our core modeling, on the left you can see the model that we created within Kino. This model is for the Polestar Core 9-2. Currently this is not the core configuration that we have for the Polestar. This configuration has 2 6% assemblies shown in red. And what we had to do first was validate this model. So what we have published right now for the Polestar is a K effective of approximately 1.02. When we did our model and calculated our K effective, what we found was approximately 1.08, and we did realize that this is significantly different than what we would be getting if we were just to model the regular Polestar's configuration right now. But we were able to determine that for our purposes of figuring just a production capability for the future, for this future design, our model was good enough. And also, when we were doing our modeling within Kino, the material inputs that we had did not account for any burnup, which is used for the Polestar specs currently. So, and we also did not model anything such as the rotating exposure ports or any of the beam ports in our core, which would reduce the total K effective. Once we had our model, our next step was going to be figuring out where we could place this model within the core. We already knew that the core was going to be small, and for our targets, we would have to remove an assembly if we were going to do it within the core. And to determine the best location with an assembly removed, what we did is we ran simulations by removing fuel assemblies. After the assembly was removed, what we did is we replaced it with just a moderator column. We discretized this moderator column axially into approximately 24 segments. And what we did is we ran our simulation, found the flux through that moderator region, and then also determined where within that moderator column we would have the highest flux. After we accomplished that, we moved on to the next assembly and sequentially moved our way throughout the core until we figured out where our highest flux would be and the best location for our production capability. Something to note here is when we discretized the moderator column axially, we discretized into, we tested against 3 components at the same time. And what I mean by that is when we were checking for the max axial range, we checked 3 positions at a time, which is similar to the height of our target, just so we could have the best production capability. So from this, the resolution is not great on the screen, but what we were able to do is produce a flux map for our core. When we removed the assemblies, we calculated the flux in that region and then plotted it here. And as you can see, or maybe not, we were finding the best flux in assembly D3 when we removed that assembly. And also, we also saw high flux within assembly C4.
So having found the location we were going to put our radiation assembly, we then modeled our target and its holder and placed it in the core. We ran tests at both D3 and at C4, as mentioned, and we found that we got a better reaction rate in C4, so that is where you can see our target. We did, however, by placing the target there, pulled a lot of fuel out, which meant we had a lot of moderator, which meant we were getting very high peaking factors. So in order to combat this, one of the primary things we were focusing on was adding something around our target to minimize peaking. On the left, you can see, okay, colors don't show up. On the left is void rods, which just hollow rods similar to the radius of a fuel rod to reduce the moderation. In the middle, we have helium rods to do the same thing. And on the right are absorber rods. The absorber rods contain helium surrounded by a thin layer of absorber, which is the same material as our control rods, cadmium, chromium, indium. And by doing this, the void and helium rods did reduce our pellet power peaking, but not sufficiently to reach our safety margins. But the absorber rods were more than sufficient. Here you can again see our, well, you can't, but there's the absorber rods surrounding the target, and here you can almost see the target in a profile. Also of note is the different colored fuel rod there is how we tested our pellet power peaking. We basically, similarly to the discretized moderator rod, we discretized a fuel rod into 25 elements, each pellet, and we ran a full simulation and determined the reaction rate in each pellet and used that to determine the peaking factor. We ran that in all the fuel rods around the target to find the maximum peaking factor. And then doing that, we tested different absorber thicknesses to find both the reaction rate in the target and the pellet, or the maximum pellet power peaking factor we had in the core. We did this to maintain a power peaking less than 2.54, our safety limit, and to maximize our target production rate. As you can see, the effect of changing our absorber did not have a particularly significant effect on our target reaction rate. So we found approximately 0.19 millimeters of absorber surrounding those rods was sufficient to give us a lot of margin on our peaking factor and give us very similar to our maximum target reaction rate.
So an important aspect of our project was to ensure that our model behaved within the NRC's constraints in the event of an accident. So the first accident that we analyzed was a reactivity insertion accident in which we assumed that the full worth of our target was dropped instantaneously into the core. This was calculated by two steady state calculations to find K effective, one with the target inserted and one without. And from that, we calculated a target worth of approximately 255 PCM, which falls within the pole-star reactivity limit of a movable insertion of 300 PCM. Another aspect of this accident is the power transient that results from it, and we calculated that using the N-hour equation, and we took a conservative approach to this, and we assumed that the target insertion was a 800 PCM insertion, which approximately splits the difference between the actual worth of our target and dropping a whole fuel assembly in. And using the N-hour equation, at approximately 0.2 seconds after insertion, we saw a power peak of 700 watts, which falls within the safety limitations. And here's a graph of that, and we have the N-hour equation on the right. And the reason we cut off at 0.2 seconds is because at that time, that provides sufficient enough time for the control rods to scram and cut power. The next accident analysis we did was a LOCA accident. Now, because Kino is unable to do transient analysis, we did this analytically using convective heat transfer with natural circulation air and conduction. And from this calculation, we saw that none of our target materials approached their melting temperatures, so we deemed that none of the limits were exceeded. And the final aspect of our project was the economic feasibility of the production. And by assuming the Polestar was operating at 2 megawatts, we found that we could produce 34 six-day Curies in a week. Now, so that provides us with a potential revenue range of approximately $11,000 and $4,500 per week. Comparing that to the cost was pretty difficult. We contacted multiple industries and institutions to gather information on the cost of a target. We contacted Missouri and we contacted the Department of Energy, and we found that costs for something as proprietary as producing moly was proprietary. So what we did was we got together the raw material costs, and as you can see, that was pretty insignificant. So if we assume that the cost of our target we talked about was near the price of a fuel rod, that would allow us to set our price that we sell our moly at just to break even with that, which makes in conclusion, makes the project feasible. So, any questions?
some questions for this group. Yes, I know.
Questions. Alan Eisenhower, Oak Ridge National Lab. On your cost, you mentioned you just assumed the cost of the target and near fuel rod. Did you look at the cost of processing? Because that's kind of the total
Yeah,
cost of supplying.
we brought that up to our advisors, and they did not indicate that we needed to pursue cost of, like, we asked about operational costs. We wanted to find out numbers on typical operational costs of the Polestar or fuel costs, but they said that wasn't necessary for it.
If you need to process it, we can do it for you. And it'll be cheap, right? Oh, yeah. The other question I asked, when you first started looking at this, you looked at Moly 98 versus ISALU, and you said you looked at, I think you said you did it on a cross-section basis to kind of do a selection. Did you consider other factors in that, like availability of Moly 98? Maybe there's an enrichment cost, but, you know, but what, were there other factors that you considered, or was it just the cross-section comparison?
The cross-section was definitely the primary factor we considered, because I said the graph of ACU uranium mass versus LU uranium mass, and then if you throw in MO98 looking at that same type of graph, it ends up being in the 500 kilograms worth of mass, which is not going to be nearly possible at all to make any amount of anything. So, and so here we're making 3460 curies with 7 grams of uranium. If we tried to do that same thing with MO98, we wouldn't even be making 160 curie, which means it's really not possible at all.
And just one thing to add to that, a consideration for this was that since we were designing it to the Polestar reactor, we're topping out at 10 to the 13 for our thermal flux, and for considerations with Moly 98, those would have to be much higher to accommodate.
Other questions, please? More? Yes.
So I'm Kevin Quigley from the Department of Energy. Looking back at your absorber thickness slide, there was a nonlinear relationship it looked like between the peaking and the absorber thicknesses used. Could you explain that trend?
Part of that was due to the fact that we had to run a Monte Carlo simulation on our personal computers during the school semester, so there was some variability in our runs. And also, but we did notice there was a particular peak, I believe it was around 0.2 millimeters of thickness, that even doing multiple runs with multiple, different random seeds, we did notice there was a peak there. So we aren't entirely sure what the physical cause of that is, but we did notice that there is a peak, and at actually smaller absorbers, we can get a lower peaking factor.
Other questions? Any more? Well, let's thank the group again.
Forward.
Okay.
Have fun.
Thank you.
Yeah, yeah.
Will I? I'm not tripping Sue.
Go ahead. Yeah.
You want me to go? Okay.
Yeah, please. Start.
Thank you all for coming. My name is Jake. With me up here is Irfan, Gabriel, and Ashley. Unfortunately, our friend Hakan couldn't join us. He's taking a final, so everybody wish him luck. Hopefully he can meet us after a while. I would just like to say our project is the design for a critical benchmark experiment detailing sodium cross-sections in liquid metal fast breeder reactors. And this is a collaborative effort between North Carolina State University, Los Alamos National Lab, and then TerraPower as well. So what we want to try to do is we want to design a benchmark that evaluates the sensitivity of K-effective to sodium in these types of reactors. So we broke this up into two different sections, if you will, with the first be modeling an existing prototype. Once that system is successfully modeled, we then take that sensitivity analysis
and then design our benchmark to that, ensuring our configuration is critical and it does indeed match the same sensitivities. So the motivation for our project comes from TerraPower's traveling wave reactor. Some key features about this reactor is first, it's sodium cooled. It features a uranium and 10% zirconium metallic fuel. This allows for an extended period of time in the core, which gets us a 40-year lifetime. Then that's achieved with no refueling, and they manage this by reshuffling the fuel periodically, typically around 18 months to 24 months. We'll show you another slide on that next and go a little bit more in depth with that. This longer radiation period results in about 35 atom% uranium and plutonium depletion. Compare that to a typical light water reactor of around 8%, so we're really utilizing a lot more of the fuel. Well, excuse me, we're not, TerraPower is. Another key feature to this reactor is its proliferation resistant, and they do this on the front end and the back end of the fuel cycle. They manage this on the front end by utilizing depleted uranium. So this minimizes our need for enrichment technologies. And then they manage this on the back end by this breeding and burning of plutonium over an extended period of time. You end up with a higher concentration of plutonium-240, which has a very high spontaneous fission reaction rate. So that's undesirable in weapons-grade plutonium. Typical values for this concentration is less than 10%. What's discharged from the TerraPower reactor would be around 30%. So this is really not an option in terms of any weapons. So to expand upon the actual breeding and burning process, we've got a neat little animation for you to follow here. How this is drawn on through the 40-year life is the depleted uranium blanket is reshuffled into the center of the core, out from the periphery, and this maintains criticality throughout this 40-year lifetime. So we've talked a little bit about the traveling wave reactor. Let's spend some time on cross-sections. So cross-sections are measured. They're measured values. And with that, there always comes uncertainty with measurements. So benchmark experiments are designed to reduce the uncertainty in our measured cross-sections. Okay? And this is done in the real world by building a critical experiment and then taking this experiment and modeling it. Once you get the model, you get a calculated K-effective, and typically what you find is that K-effective is not equal to 1. So then cross-section evaluators go back and tweak the cross-sections until they get a K-effective of 1. Looking to the table over here on our left, this just shows some previous sodium benchmarks. There's only 6, so this is a relatively, there's not many of them, I should say. And if you'll notice, I did say on a previous slide that our fuel in our TWR is a uranium zirconium metallic fuel. None of these have been done on that. This is all MOX fuel and UO2s. And to show you guys what a typical sensitivity plot looks like, because we've got some of those coming for you. Spoiler alert. We've got an energy range here on the bottom. It's in a logarithmic on the horizontal axis. The vertical is sensitivity per unit lethargy. And you'll notice here, well, it's very difficult to make out. This is blue, and this is the elastic scattering cross-section for sodium at the sensitivity there. The red, the side of it here, is the inelastic. And next, I'm going to let Irfan come up here and talk to you guys a little bit about some sensitivity calculations and analysis.
So it seems like every fourth word in this presentation is sensitivity, so it's important to actually understand what we mean by sensitivity. So in a general case, sensitivity is simply how a relative change in a system parameter, for our case, that's going to be sodium cross-section, how that relative change results in a relative change in a response variable. For our case, that's K. So the reason this is important for us is there's something called the K-Sen card, which is implemented in MCNP. This was done by Brian Kudrowski, and the way he did this was using perturbation theory. So this sensitivity coefficient, again, it's a ratio, but now the ratio is of adjoint weighted integrals. So this is a bit more complicated, so let's quickly step through the sensitivity coefficient. So in the numerator, we have these brackets. Those simply just denote integration over space-time energy. Our first term right there is going to be the adjoint angular flux. Then we have our production minus the loss terms from neutron transport theory. That first term, kappa sub x, is in scattering, with the sub x being sodium. Then we have fission of sodium. Obviously, that's going to be 0 for us. And then we have the total scattering, the total cross-section of sodium. And then in our denominator, again, it's just the inner product of the adjoint angular flux and the fission operator of our entire system. So moving forward, so now we can see a visual of what TerraPower's TWR core looks like. So the center orange circle, then the purple and the light blue are all just different fuel assemblies of different enrichment. The dark blue is HT9 steel reflector. The reason TerraPower chose HT9 was because of its ability to withstand swelling under large amounts of irradiation. When you have a 40-year lifetime, obviously you're going to have a lot of irradiation. So now we look to our sensitivity plots. So as we can see, we maximize our elastic scattering sensitivity in the 0.1 to 1 MeV energy bin. Following that, our flux, once again, is maximized in that 0.1 to 1 MeV energy bin. And our fission rates for 235 and 238 uranium are comparable in that 0.1 to 1 MeV range energy bin. So when we talk about our comet criticality experiment moving forward, keep in mind that we're trying to get to as close to these plots as possible. So now let's talk a bit about homogenizing the TWR core. So as we saw in the previous picture, there's a lot of fuel assemblies. Specifically, there's 271 fuel rods per assembly with 279 fuel assemblies in the core. That's 75,609 fuel rods total. So what we mean by too many cells is MCNP can handle this, but that time is extremely long. And when you're dealing with a senior design project where you're always tweaking the design a bit, you want to minimize that time as much as possible. So we homogenized. The way we did that was averaging by volume. And of course, we need to make sure that actually works. So the blue, as you can see, is homogenized assembly, with the red being pin resolved. And our elastic scattering sensitivity, they're very similar. Our inelastic, even though they're not similar, as you can notice, we're maximized in the 0.002. That's the maximum value, while for elastic, it's 0.03. So we're most sensitive for the elastic scattering cross-section, which is what we're going to be interested in moving forward. And the flux spectrum, as you can see, are practically identical. So just some more things about TerraPower's TWR model. So the way we found the critical configuration was using nonlinear optimization. We used the Broyden-Fletcher-Goldfarb-Shannon algorithm, more commonly known as BFGS. And the reason we used that is we weren't interested in minimizing K effective, but the distance between K effective and 1. So first we had to find our central uranium enrichment. We found that to be 7.15% for uncontrolled K effective, equaling to 1.03 at startup. What we mean by uncontrolled is all rods out. And the reason we went with 1.03 is because you need a little bit of that excess reactivity at startup to be able to power on the reactor. So second, we found the critical control rod position. We found that to be 1.07 meters withdrawn. Now, Gabe will talk more about the Comet criticality machine.
In order to perform our experiment, we'll be using a machine called Comet. As you can see, the Comet machine is actually a very simple structure. As you see, it has a support structure, a stationary platform which you will stack your materials on, and a drive assembly which will raise material to meet the stationary platform. And the picture next to this is just an image of the Comet machine, and the scientists are performing another similar criticality experiment. Materials that we had to use for our design. For the design, that most of our material are actually from old experiments, such as our highly enriched uranium plates and our natural uranium plates. As you see, that they actually come from something called the Jemima experiment. The sodium plates are from an experiment called Zipper, and they're more into tiles. Also, most of these plates and tiles will have a diameter of 21 inches, so they're not really that big. Also, in the design that we have polyethylene plates. For our experiment, we had to have a cost. Basically, they gave us a cost to be on budget of, and our cost was actually $500K. As you see, that we actually went a little bit over that, but some of these costs will be supplied from other sources. one of the costs was the experiment cost, which is about $135K per week. The proving and the planning stage, which is about $10K per week. We had to fabricate some of our materials, such as the polyethylene plate, which we got a price from that from a company called Shieldworks. Aluminum frame fabrication, which the price was provided by the Precision Machine Shop, which is located in the basement of Burlington Labs, and an analysis support, which costs about $10K per week. Some of the design restraints that we had to conform to, which some of the design restraints that we had to one was we had to make the configuration with access reactivity. The reason for that is because we have voids throughout our configuration. The sodium sensitivity had to match that of the TWR reactor. And for the Comet machine, we had to be within a weight limits. 20,000 pounds for the top platform, and 2,000 pounds for the bottom platform. And now I'm going to let Ashley take it over with more of the materials.
So using those criteria and the materials provided, we began our fuel unit design process. We started off with a simple unit of HEU plates all stacked together. That was highly subcritical, so we put a 1-inch axial reflector on the top and bottom, still subcritical. Then we took a cue from the Zeus experiment that you saw a photograph of a few slides ago, and they had a full copper assembly around the entire fuel unit. And we tried that, and we're still highly subcritical at a K-effective of 0.819. And also, when we analyzed the K-effective sensitivity to both copper and sodium, we noticed that it was more sensitive to the copper than it was to the sodium. And that's not what we wanted. We're trying to create a sodium sensitivity experiment, not a copper sensitivity experiment. So we fully removed that copper reflector assembly, and we kept the HEU, we decreased the thickness of the sodium to 1/4 of an inch, and then we added polyethylene into the mix. And the reason we added polyethylene was because we needed something to moderate our fuel unit assembly, but not moderate enough to where it went into a thermal region, because we're trying to model a fast reactor. It needs to remain in the fast region. And then we also have a large sodium reflector around that. This gave us a K-effective of 0.901, so still subcritical. We further remodeled it and got some advice from our industry advisors, and this is what we came up with. We still have the same HEU 1/4-inch sodium and polyethylene plates, but we added a dual reflector of natural uranium and sodium on the top and bottom. And this brought us supercritical to 1.034, and that is good. We wanted, as we said before, we wanted enough margin to account for the voids that will be in the physical Comet experiments that we can't necessarily account for in our MCNP model. And those voids will bring down our K-effective value, down closer to a criticality of K-effective equals 1. This is a look at our individual fuel unit. We have sodium with alternating HEU and polyethylene, and we have 5 repetitions of those within our fuel stack. And you can see the natural uranium and the sodium on the top and the bottom. Here on the left, you can see our further refined model. And well, actually, it's our final Comet benchmark model. We added further detail to include components of the Comet machine, such as the diaphragm, the platen, and the alignment tube. And we also included the aluminum frame, which we will have fabricated to surround the sodium tiles. And the sodium tiles were all compiled together to create as close to a 21-inch diameter disc that we could. And so that's why the aluminum frame is in there, to keep the sodium tiles from moving over the course of the experiment. And each of the sodium tiles are also clad in stainless steel 304 to prevent the pure aluminum from reacting with the air around it. On the right, you can see our scattering sensitivity, flux, and fission rate plots for both the Comet benchmark and the TWR. Looking on the top plot for scattering sensitivity, the red line that indicates elastic scattering is maximized in the 100 keV to 1 MeV range for both the Comet model and the TWR model, and that's exactly what we wanted. We wanted them to be completely matching so that they would be able to relate to one another. The flux plots are both watt spectrums, so they're both for fast reactors, which is what we're aiming for. And then the fission rates are similar in trend. They simply begin in different energy bins, which is okay. Here we have a visualization of our comet model that we designed in MCMP versus the actual comet machine. On the top portion of the diaphragm and above will be on the stationary platform. That won't move. The bottom portion with the alignment tube and the platen will be on the movable drive assembly, and that is what will move during the experiment. So how the experiment will be done will be that an individual fuel unit will be placed on the movable platform. That movable platform will be raised up into the stationary platform. A neutron count will be taken, a plot will be put on a 1/m curve, and then it will be lowered, and that process will be repeated until a K-effective value of 0.9 is reached. And that is when the hand stacking will end, and the remaining approach to criticality will be done remotely for the safety of everyone involved. And finally, we have our very own 1/m approach to critical. We did this versus the separation of the top and the bottom portions of our MCNP model. We came to criticality at 75 mils, or 75 thousandths of an inch. And on the bottom, you can see an animation of our model closing together with the relative K-effective value. So in conclusion, we successfully modeled a traveling wave reactor in MCNP, and we obtained the sensitivity of K-effective to sodium for that model. We modeled our benchmark in MCNP as well, and we successfully maximized it to we successfully maximized the sodium sensitivity in the same energy bin as the TWR, which is the 100 keV to 1 MeV range. And we also created a 1/m versus separation distance curve for our model. And we're proud to say that there is a high likelihood that Los Alamos National Lab will implement our design in a future experiment, and that will help further the development of liquid metal fast breeder reactors. We would like to acknowledge Los Alamos National Laboratory with Justin Hutchinson and Jordy McKenzie for helping us, and also Nick Turan from TerraPower. These are some references if you'd like. Do you have any questions?
Thank you. Questions for this group? Questions? Yes.
Yeah, that would be,
Yeah, sure.
Jake would be able to answer that.
Let me go back to that table. Bear with me, sorry. There's a lot of slides. There we go. You're talking about this table here? Okay. So that was with, let me make sure I get this correct. This was sodium as a coolant, right? That fuel type and yes, that's where I got these experiments from. Sorry, I can't hear you.
So it's called reactor physics handbook. I don't know if you looked at this.
I did not.
So there are more experiments with sodium. And also, I'm not sure that you look at the experiments performed on CPPR and ZPR facilities that existed some time ago in hardcore machine lab.
Yeah, that's where our sodium tiles came from, was the zero power physics reactor.
Okay, but there are much more experiments available which are not in the handbooks.
Okay, that's where I got those.
And I'm pretty sure that in this experiment you will find experiments with a sensitivity similar to the TerraPower reactor sensitivity for sodium.
Not according to Los Alamos.
Okay.
Thank you.
Any other question? Any more questions to this group?
Yeah, sure.
Oh,
Yeah,
thank
no
you.
problem.
Thank you.
One last experiment that you had a sensitivity to elastic and inelastic scatter calculated with MCNP.
Yes.
And this sensitivity is very small.
Other questions? No questions? Let's have thank the group. Let's take 15 minutes, just, a break. 15 minutes. We have 3 more presentations. Okay. Yeah. 15 minutes.